Hey guys, Paul from Paulskarts here. Just wanted to make another little quick video. I haven't been making videos in a while, and today's Sunday, so I have a little bit of time on my hands. Figured I'd make a little video. It's lunchtime, taking a break. So have a couple cylinder heads here that I've been doing since Friday that are going to ship out Monday. So while I had one of these cylinder heads here, I figured I'd make a video on it, and this is actually a really cool cylinder head, seeing as though it has the Mold Star seats, welded intake tube, and has the big valves, 3228, and has all the bells and whistles. You know, it's ported by me, bronze guides, polished chamber, radius unshrouded chamber. So I figured this would be actually a great head to kind of talk about. And what I was actually thinking I wanted to talk about was some key features that really help a cylinder head shine when it comes to making power and overall longevity and the ability to maintain that power for a long period of time without failure. So I know that sounds like a bunch of different topics, so it's not going to be really extensive on each one, but I've gone through and listed some of the line items basically that we incorporate into this head so in the past. So I figured I would go a little bit more into detail how each one of those things kind of benefits you and benefits making power, and in some of them how they basically allow you to make that power for a longer period of time. And basically what I'm talking about when I talk about that is the seat material. I don't know why I just use this thing as a pointer. It's just a welding rod, so I just had it laying here on the bench, so I figured I would just pick it up and use it real quick. So we could probably start off with just the casting, and this is the casting I use. When I'm talking about the casting, I'm talking about the head itself. There are different types of casting. There's Hemi head casting. There's a Gx200, which is the same as the clone castings, which is the same as like the Predator 212 stock casting, non-Hemi. And then you have like the Gx160 castings like you see here. Now the difference between them is, let me see if I can find something. This is like a Hemi head. This is actually off a Wildcat. You can see the port on this thing. These are pretty cool heads, actually. Here's the port on the Wildcat. Extremely small in comparison. There's my pinky. That's the Wildcat head. That's the port there. It gets up to my pinky first knuckle there. So that's a Hemi head. As you can see with a Hemi head casting, this is like a dish. There's a lot of surface area in there, big CC volume, not ideal for a smaller engine. This will probably give you like 8.5 to 1 compression ratio, something like this on a 212. These do have their place though. So that's like the Hemi head. Then you have a Gx200 casting, which I can show you now. So a Gx200 casting looks like the casting you see there, which is a Gx160 casting, but it just has a bigger chamber. You see how big this chamber is, especially down in this area? How much larger it is? Everywhere. There's just more up here, there's more down there. So this is actually a Tillotson casting. So these here would be a 22cc chamber compared to like a 14cc chamber there. So you have the three different castings as a starting point. You have a Hemi, big chamber, non-Hemi, big chamber, and then the Gx160 14cc casting. These are actually very hard to come by these days. I've been calling all around everywhere. I bought the last of them everywhere I can find. I'm only selling them in complete form. I'm not doing the just seats installed anymore because they're saying 2 months till they come back in stock anywhere. So I'm kind of holding on to those for dear life. So when selecting the head casting you want to start with, what you want to kind of think of when selecting that starting point is your bottom end volume. Are you starting with a 212, a 225, 236, or a 266? This casting size was going to pretty much right there off the bat depict your compression ratio. There's a couple other factors, but that cylinder head is going to be the main decider. Besides that, you know, head gasket thickness and piston placement relative to the top of the bore, whether it's in the hole or out of the hole, and if there's valve reliefs on the piston will depict your compression ratio besides the cylinder head chamber. So the cylinder head chamber is the largest variance in that normally. If the piston was in the hole, you know, 400 thousandths, that might take the cake, but you'd never see a setup like that. So first thing you would do is select the chamber. I like the Gx200 castings for their smaller chamber size. They give you right off the bat that torque. That smaller chamber, that higher compression ratio is going to give you that torque. I might as well see if I can put some of these other castings in here so you can see them as I'm talking about them. So this one here is going to give you the most amount of torque because it's going to have the highest compression ratio. The highest compression ratio is kind of ideal. Now the reason compression ratio is ideal because compression ratio, and we could really go down a black hole on just compression ratio alone, so I'm just going to skim the surface of it. Compression ratio has to do with a lot of things. Usually it has a direct correlation to the duration on your camshaft. So most camshafts that are bought as a racing camshaft will tell you 12:1 or greater compression ratio required. That does say required, not recommended. Required is a requirement to make the cam work correctly. And that's where I'm going to stop on that. I'm not going to go into valve timing, etc., which would be the rabbit hole for compression ratio. But normally you would want to try to get 12:1 compression ratio on your engine, period. Now that's a static compression ratio number. So some people will say, oh, well, I run gas and gas might detonate at that. And you can run gas in these engines with the racing cam at 12:1. We do it all day. We never detonate. And the reason is that's a static number. Under the dynamic function of the engine, with the you're not using it at the bottom during peak torque at 100% volumetric efficiency, which means you're not going to hit that high cylinder pressure down low. When you use the racing camshafts, it moves everything up high, the power, so cylinder pressure down low is dropped, and that right there probably went a little bit deeper, which might complicate some of the people that are just starting off. But I do think I have other videos out about camshafts that you can probably watch that would clarify that more if you have a question about that. So the first thing you would want to do is pick the casting size that can get you to 12:1 compression ratio. Right there, that's your goal. Now once you're at 12:1 compression ratio, the second feature you would want in the cylinder head is the ability to flow enough CFM to meet the needs of the bottom end requirement, and there's a calculation you can use for that. I don't know if I know it off the top of my head, even though I use it like 1,000 times a day. I think it's like cubic inch times RPM times 0.0009 something something something, and that'll equal out to your the volume, the needs of your engine. Now when you use that equation, you want to make sure the cylinder head flows the right amount. If you pick the cylinder head, now whenever you're building a cylinder head or when you're purchasing a cylinder head, if you are purchasing a cylinder head that just has a set flow number printed on the screen from the person you're purchasing it from, you can do that equation out to know if that cylinder head falls within your engine's demand at the RPM. Now, what happens if the cylinder head flows more than your demand at a certain RPM? Say you want it to flow best on a racing engine at, normally on a camshaft, you have 1500 degrees window of power curve. So say if you wanted it to flow best at, say, 7500 RPM, that would be in the middle of your 1500 RPM window. What you would do is look for a cylinder head by doing that equation using the cubic inch times 7500 RPM to give you the CFM requirements of it. Now that you would look at that cylinder head online to see if its advertised flow rate is within your power, within your cylinder or within your bottom end volume demand, within its need. Now, if it's too little or too much, what that means is you're going to be either sacrificing power or sacrificing your homogeneous fuel mixture in the combustion chamber. Those two things get affected by port speed. Now, I've always said in my video, it's all about velocity in the ports, and CFM is nothing but just one little snapshot of that. It's just like one piece of the puzzle. But if I had to choose, I would choose velocity over CFM. And the way the head is designed for that requirement of the engine is ultimately the make or break for choosing port size and choosing the cylinder head that's best for you. Now, when I'm building these, basically you can send me your information and they get built just for your engine. So if this per se was built just for your engine, the port would flow what your engine needed at the RPM you wanted to use it at. And we would build that into the port for you, so this head would work on your engine. But if your friend had a 225 and he put it on his engine, it wouldn't be as good. And you cannot really technically swap one head over to another engine. If you do swap it over to another engine and it works better, that means it wasn't ideal for the first engine, or the combination you had put together just wasn't ideal. What you really want to do is match a head, a cam, and a carb shaft, a head, a cam, and a carb all together to flow the requirements, and for the cam to control the valve timing to make the most amount of power at the certain RPM. So everything is kind of, all stars are aligned to try to put the most amount of power at that specific RPM and still try to maintain the most amount of power before on the dyno graph and the most amount of power after on the dyno graph to maintain the horsepower for the longest period of time with still hitting that peak horsepower number. Does that make sense? So once you have the chamber size selected and you have your 12:1, if I'm running methanol, usually I like to set mine up at 14:1. So usually I'll take this cylinder head and mill it down. Now on some of the bigger stuff, like when you get into 72 millimeter strokers, this head in 14cc size as is will give you 14:1, maybe more, depending on the head gasket you use, which is right where I like to set it up for methanol. 14:1 on gas is a little much. Okay, so after you find your compression ratio, select a cylinder head and have it milled or decked or whatever you need to do to get it to the 12:1 or get it to the 14:1 for compression ratio for gas or methanol. Then you've selected a head or had the head builder build your port and select your valve size to the size that meets the requirements of the bottom end. Those are the main two components of the engine. Now on this, we've added a welded intake tube. Now this welded intake tube allows us to get more CFM through the bolt area, because if you look at this bolt area, if you have to bolt the manifold on, the manifold is going to come like this, right? In this area. The tube we use comes up here, over here, down here, and over and around here. We have to weld all this in order to get the tube big enough so we can open this up. Now, the reason why that's so important is, and the reason why this makes power, this is why this makes power, because everything has to transition as a taper from here to here, and this being the smallest point. Now, I just kind of watched a video that showed the port flow dynamics and everything like that, and when I watched it, it made great sense, and it kind of made everything click that, you know, when we were testing all kinds. Now, we have a flow bench, we have a dyno. Back in the day, we used to flow smoke and liquids and stuff through a clear flow bench to watch the patterns. I think that video is still on YouTube. And we still velocity probe and all that stuff. And our research always showed that that a higher velocity port made more power on the dyno. Now, here's the thing. Here's the kicker. You can have a port that flows 100 CFM and another port that flows 100 CFM, right? People talk about flow numbers all the time. You could have two ports that flow 100 CFM. One port, it's not hard to get CFM. All you have to do, any fool can get CFM. All you have to do is get in there and destroy stuff and make it as big as possible, and poof, CFM. It's that simple. So you can have two heads that flow 100 CFM. One head will make more power because it flows the 100 CFM and it flows it at a higher airspeed. And that's the key to it, velocity. If the air speed does not start filling the cylinder the second the valve opens, the time it takes to start that air and fuel moving is going to kill everything under the curve and after the curve for peak power. Now, 100 CFM and 100 CFM will make the same peak power. You could have a bad port and a good port, 100 CFM, and they'll both make the same power at peak power, at that peak RPM that you designed it to make peak power at. Say if it's 100 CFM on a 212, it would make peak power at 7,500 RPM. Now, if it made peak power at 7,500 RPM, what does the torque curve look like before and after? A bad port will literally just fall on its face right off the line. And you cannot do anything to get power until peak power. That's the difference between a port that's designed correctly and a port that isn't designed correctly. So don't be fooled by CFM numbers. They're very easy to get. And you cannot beat perfect. I cannot emphasize that enough. You cannot beat a head like we build here that is built to the math. Do not be fooled by a CFM number. Do not be fooled by somebody that does not test. Do not be fooled by somebody that does not have the equipment. Do not be fooled by somebody that has some style to their selling point. The only thing that matters is results on the track. So you have the chamber size selected. Now you know how the ports are selected in size through an equation. The bronze guides here are built for longevity, lubricity factor, and will help your stainless steel valves reduce friction while they're moving, and will help the longevity of the valve guide. They will definitely maybe not show horsepower, but they will definitely maintain a better valve guide for longer. The valve seats are, now let's get into the seats. The seats alone are a huge talking point. The reason they're a huge talking point is because the seat depicts a lot of things. The seat ID is what you base all of your down port sizing off of. So everything flows down and out away from the seat ID. The seat also, you have a seat ID and a seat OD. So that seat width is important. The seat also has angles on it. The seat also is made out of a material that has different hardnesses. Different hardnesses can either produce or reduce valve bounce. Different materials can either enhance or support valve heat and the removal of the heat from the valve into the casting, extracting the heat out of the valve and into the casting. The material can also expand width less than or more than the aluminum material. So if the seat expands less than, like a hard steel seat, expands less than aluminum, that means that seat can get loose at high temperatures. When the aluminum expands more, can loosen that seat and the seat can fall out. Some people don't have the capability of installing seats as well, and we actually use seats that do not touch in the center anymore. I know a lot of people are starting to kind of follow that trend that we started, and I'm hearing that term used more and more, non-touching seats, in people's descriptions. Usually they kind of just watch the videos and follow the trends we set here. The seat angles will depict the amount of flow in and around the seat. And I cannot emphasize enough how important back angles are too on the valves. Cutting back angles on the valves and having the correct angles on the seat are guaranteed horsepower, period. You are going to pick up at least a horsepower just by having the back angles on the seat, on the valve. If you cut a back angle on the valve, you'll gain a horsepower. If you have the seat angles on the seat wrong, you could lose 2 horsepower. If you have the wrong size seat for your flow requirements of the bottom end, you could gain or lose big horsepower, because this depicts all of the port. So what else is about the seat? Oh, this radius cut here. You see this cut here? You see how there is no ridge? And I've been doing this for a long time. There is no ridge here. There is nothing. You can't even tell where one stops and the other starts. This seat transitions perfectly into this tight radius. Now, what I just found out why this works so well, I've been doing this for a while, and just knew, I always thought it was just unshrouding the valve. But another reason why this works so well is this is actually keeping and maintaining the velocity around the valve as the air exits. You can't just dump the velocity. If the air comes out the valve and it's just a big open port like this and just dumps, what's going to happen is it's going to just go turbulent the second it comes off the seat. All of those radiuses, those nice, and they're everywhere on that seat. You can see they're everywhere. They're 360 degrees around that seat. That radius, as the valve opens at low lift, maintains the airspeed in and around that valve with the Venturi effect. And that's also why, what I just found out again, what we've been doing for a long time, is why the back cuts are so effective. Because they tune up that Venturi effect. Now, I've been doing a lot of this stuff for a long time. And I knew what we were doing worked. I just watched the video and heard this guy describe this stuff. And now I know why even more. And I'm a pretty smart person. We do a lot of testing. I do a lot of testing. And now I know the reasons behind what I do worked. I thought this made more power because it was unshrouded, which is a big part of it. But you can unshroud this just with a nice square corner and a big ridge. The way I do it, it holds the velocity around the valve. And that's another reason why this is so effective. So if you look at this head, it's got the small chamber. It's got the right size seat. Bronze guy. It's got the right size port. It's got the right manifold. Right seat angles. It's got the right radius unshrouding. It maintains that velocity factor through this tapered area after the seat. This here is the ideal, 100% ideal intake port track. 100%. To the math, perfect for the engine, with the highest velocity speeds we can get, meeting the CFM requirement for the bottom end, not going over, not going under. This is with the best seat material, with the best seat angles, and this perfectly non-ridged area, with the seat sitting on the, with the valve sitting on the seat at the perfect area, sealed 100%. Ideal scenario. That's what you aim for. So if you were going and you were making your pre-build build list, you would say, I want 12-to-1 compression ratio. You would do the calculation to know how much CFM you required, put that down. You would say, okay, if I require this much CFM, I need this size seat. I need this size port. I'm going to be turning a lot of RPMs. I'm going to need bronze guides. I'm going to be using gas, or it's going to be getting real hot. I need a nice seat material, or this seat material is just great because it deadens bounce, has a high internal friction, it deadens bounce, valve bounce. So when you start making your build list and start putting all these boxes that you're looking for or requirements for your engine, then you call me and say, hey Paul, I need this head. This is what we spit out. This cannot be beat. If it is 100% sealed through leak down tester, meaning you're not having any ring seal problems, valve seal problems, cracked block, cracked sleeve, leaking head gasket, spark plug crack, cracked cylinder head. If you're not leaking any cylinder pressure down, this is as perfect as it can get. Built by the math, with science backing it, by a professional, with all of the best tools. Well, I don't know if they're the best tools. You can always get a better tool. I'm not going to lie. You can spend big money on tools. But every tool required to build this perfectly. And test it, flow test it, dyno test it, velocity probe it, vacuum test the seat, measure the ID with the ball gauge, with a small hole gauge, and get this tuned up perfectly to your engine. The Ferrea Racing titanium valves would have topped this off. This is the valve train this customer is getting, stainless steel valves. If he had gone with the titanium Ferrea valve train on this cylinder head, it would have been the perfect package, because those valves have back cuts, they're lighter, they're titanium, they go perfect with the Mold Star seat. Just an amazing product. But these are the heads that we're putting out. You know, we do a lot of them. Here's one here with an epoxy port. We've been really, I don't know why, but these Mold Star heads have been flying off the shelf lately. Guys, we are sleeving engines. These are sleeves, ones for the deck extension. We do big blocks. You want your 600cc big block, call me. 3-inch bores. I know the blocks aren't out there right now. If you guys need a 3-inch bore, they made the order. It might take you a couple weeks, but I don't think Tillotsson's making those sleeveless blocks anymore. So ring-a-ding-ding. You need it, call me. I know the main guys are out of them. But yeah, hope you guys took something from this 30-minute video. If you guys want to get in touch with me, I'm Paulskarts. You can get in touch with me through the eBay. You can get in touch with me through the website. Website is paulskarts@gmail.com. Oh, sorry, that's my email. Website is paulskarts.com. If you want to email me, the email is paulskarts@gmail.com. What else is there? Oh, you could either text or call me. The phone number is 781-492-7358. Again, 781-492-7358. I'm Paul. This is Paulskarts. Hope you guys enjoyed this video. And until next time, guys, have a nice day.